Hello everyone, this is the demo on battery technologies. This is the third and the last one. I'm Meysam Mehr Avaran. I've been with Ozone Engineering for more than a year, and before that I was in with an electric car company called Byton, and before that I was almost 5 years with Ford Motor Company. What are we? We are Ozone Engineering. We have been in the Bay Area for 17 plus years. We have 1,000 plus happy clients, and we sell ANSYS products. We do customer support. We conduct trainings, and on top of that, we do some projects as well. We do sell a lot of simulation softwares, which includes multi-physics, finite element analysis, or FEA, computational fluid dynamics, electronics, and electromagnetics, including high and low frequency. And as I mentioned, we have been the elite channel partner of the year for ANSYS several times, and we are proud of it. This is the list of softwares that we can sell and do training for you. We have a lot in structures, for example, mechanical, autodyno, LS-dyno, ENCODE. In fluid category, we have Fluent, CFX, and also Polyfluent, etc. On electronics, we have Maxwell, HFSS, Q3D, and all the high and low frequency tools that you see here. On some semiconductor industry, also we have tools like Pathfinder, Red Hawk, etc. Some on Optis, and except these categories, we also have some other categories. One is on materials, which is Granta. One is about embedded software, which is mostly SCADE. And the other one is Twin Builder for system level analysis and Medini Analyze for functional safety specifically. So as you see, it's a large number of tools in different categories. So whatever you're doing, feel free to ping us. For sure, we have a tool that can help you and make your job easier. The outline is that we'll go over the market research, do some study, and also the new battery technologies. This is what we did in the first YouTube short. In the second YouTube short, which was the previous one, we did some study on reduced order models and digital twin and how to model batteries inside digital twin. Also, we had a touch on BMS and how ANSYS deals with it. In this YouTube short, which is the last one, we'll go over system level modeling, which is mostly in Twin Builder, and also on top of that, we'll have an example of a battery pack with a fan and a switch. Then we go through the problem step by step, so you have a better sense of it. System level modeling, it's very important. It's important how you model a complicated system which has, let's say, 30 parts in it, like the electric powertrain in a car or in an airplane. Each of the components might be acting really properly on themselves, but it's important to act appropriately as a part of a big system as well. On top of that, we need to be able to predict the dynamic behavior of a system, which is made up of several components, because that's what is more important rather than just the individual parts themselves. The other important topic is optimization. You want to make sure that you optimize for the parts and the part in a system does its best job. And it can deliver the total role of the system. And finally, the other thing is the tuning and calibration. You want to make sure that the control mechanism in each of the parts is well defined and it's well tuned and calibrated, so the whole system can deliver its role properly. For system level analysis, definitely we have that capability, and it's in Twin Builder, which is an analysis tool. Here we see the closed loop in a car. As you see, you have battery, you have powertrain, you have BMS for the battery, you have heating and cooling, and it could be more and more complicated. You have software in loop, This is something which can be easily done inside Twin Builder. You can connect the parts together and let them operate at the same time, maybe do a transient run and see how the whole system acts holistically. The key benefits are that first, you can optimize component selections to improve the system performance rather than just the component itself individually. The other benefit is that you can validate the correct response versus functional requirements. So you can make sure that the whole system satisfies the, let's say, requirements you have regarding functional safety or system requirements. And finally, you can tune and optimize control system inside the whole loop. So the whole system is well calibrated and well tuned. Here's the other example, which is how you model a battery pack inside the Twin Builder. As you see on the lower part, we have equivalent circuit model or ECM for a battery cell. From there, when we connect several of them together, we can create a battery module, as you see here. So you can predict the behavior of the module, and then even when you go one level higher, we can connect several modules together as a system, and based on that, we'll have a battery pack. You see the final product on the left side. This is something, for example, that you would have in a car or in an appliance. So you have the system, but at the same time, you know how each of the cells would be behaving, which is very helpful and very accurate. As you see here, you can predict the response of the system. For example, if you have a transient run or you go through a certain driving cycle, let's say you drive the vehicle and you get some amount of torque out of the motors or get some amount of current out of the battery, you can monitor how much will be the temperature, how much will be the voltage, and all these can be predicted as you have a system level tool. This is another example which about the battery management system and integration with ECM. And also thermal model, as I mentioned, you can create in the, I think it was the first YouTube short, we mentioned that we can model a battery by connecting an equivalent circuit model or ECM, which represents the electrochemical behavior and also the thermal ROM. And then we have electrochemistry and thermal coupled model. As you see, we have both these acting, and on top of that, we have BMS. So you monitor the current and voltage through each of the cells and temperature of each cell, and based on that, you fine tune and make sure you fine tune the whole system and the whole battery pack, and make sure you work in the appropriate operation range. Based on that, you can see here that we can see what's the voltage that's happening, what's the current, what's the say the charge in each of the battery when you go through a certain cycle, and also you can predict the temperature on each of the cells. These are the benefits of system level analysis which can be done inside Twin Builder. This is another example or another demo which shows the battery charging with BMS supervision. This is a GUI which has been built, but in the background it's running inside Twin Builder, so you can see how it charges or discharges and how the temperature would change, how the current would change, and how the BMS would play its role. The previous slides were more descriptive, but after that, in this next couple of slides, we will have a small example, which is a battery pack, which is a 14S1P1 battery pack, which has been modeled inside Twin Builder. And then it's connected with a fan. It's running a fan, and it has a switch on it too, if you can assume that. And first we'll have a generic battery model. Then we'll add the fan and the switch in the loop. And in the next step, we will include a simple BMS model in it. We'll tell you how we write it, and then we predict the transient behavior of the loop based on our model. Here, as you see, there's a battery pack. This is, as I mentioned, you need to have a battery thermal ROM. You could have it as a SML model or simpler model, or we tried to get it just as an FMU. You have both options. And then you have the ECM model, which is a Modelica component here. This is built from the test data inside Twin Builder. And these two are connected to each other. They're coupled. And also on top of that, we have some external resistance added to the battery itself. And this could be any resistance. Here we have a part that allows us to put resistance as a function of time. So imagine first the switch is off, and then you turn on the fan fully open, and then you bring down the RPM to maybe 80%, and then you bring it back up. So you can impose that certain profile during this operation cycle using this data pair that is shown in this slide. This internally replicates the switch and the fan, which is running based on the current that it gets from the battery. The top left-hand side Modelica model is just something simple for heat transfer. Let's say you have a cooling plate around the battery, so it models the heat transfer based on that. And then the lower part, Modelica model, as you see, is the BMS, which is in charge of battery management system. This is something we prepared, and based on that, you can adjust the current through each cell based on, for example, the temperature they have or a state of charge. As I mentioned, the BMS we have decided to work with is very simple. Here is the diagram of the logic behind it. You can use writing the codes manually, but it's quite hard. This is more efficient to use a model-based design and using this diagram and this logic inside the Twin Builder. First of all, is simplicity, as I mentioned. Second of all, you can address if these logics are ISO 26262 compliant. Skate and other tools that we have in ANSYS can help you with that. This is a very simple BMS. As you said, you get the temperature, which is the average temperature, and you check it if it's more than a constant value. Imagine here we put, I guess, 60 degrees C. If that was the case, we go back to this box and say, okay, get the current in that goes through the battery cell, and if the temperature is more than 60, multiply it by 0.8. So if you have, let's say, 10 milliamp current going through it, if the temperature was more than 60, bring it to 8 milliamp, so you get less heat generation. So it's a very simple one. In real cases, it could be PID control mechanism or much more complicated. But as I mentioned, this is just a demo problem, so we try to make it as simple as we can. The other part, as I mentioned, is a data pair that you put the resistance. This is replacing the fan and the switch. This can take any arbitrary profile during the runtime. For example, we put this profile, which means that initially that the fan is off, then you turn it on at full power, then you bring it to maybe 80% power or less resistance or less RPM, I can say. Then you run it for some time, and then you go up to max power and then back to 80% power. So you can put any profile. It's very simple. Just put a table. You can put it manually or through a text file there. And it has the capability to take any arbitrary profile. Based on what I described, now we can predict the behavior of the system. Here you see there's results after 10,000 second transient run. You see how the losses, for example, changed in different cells as a function of time. Then you see how the temperature goes up. Initially, it goes up much faster, but almost immediately the BMS kicks in and makes it a little slower because the current is cut to 80% of what it was. And here you see the current that goes, the initial current that goes into the battery, and then the corrected one. As you see, the first one is 10 milliamp, and then after the BMS kicks in, it goes down to 8 milliamp here. And this is the voltage. As you see, there's a small spike, but pretty much it's fixed around 4.2. I think after that, let's take a look at the model itself now. This is the model as you see. As I mentioned, you can put the logic in it. Let me just show you guys. There are two models. If you wanna put for example, the logic in it, this is what I showed you in the slide. So you can put any value in it. What's the temperature? Like 60 C, and then this is the logic you have, and then you have a lot of components you can add here to put any control mechanism inside this bar. And then when you're done with it, you just compile it, and then it gives you a code so you can put in your model. We did the same thing for this one, but this is because it's compiled, I just have the code for it. The product is, it transfers that automatically into a simple code, so you don't need to do it manually. It's way easier this way. And after that, I have the FMU, which represents the thermal RAM. This shows what you have as input and output. And then I have the ECM model, which is here. So you have all these capacity, state of charge, all these parameters you can put there. And therefore BMS, the easiest way to do that is to create a simple Modelica model, as I showed, and put the logic inside that. Usually BMS has a lot of pins that connects to different components, and let's say, for example, gets the current in and then does the control algorithm on it, and then gives the current out, and then you feed that into the battery module. And here is the switch and fan representative. You see it has a data pair component. You have a resistance, which is time variable. You can easily edit it or add a new one. It's easy to do it manually. You can put any part you want in it, any number, and put any profile there. And this is mostly, I would say, for the heat transfer and cooling via the cooling plate that we have around the battery pack. Using these, then we would be able to run the model. You just simply go into, as you see here, it's running for 10,000 seconds. What's the mean time? What's the max time? And then after that, you just run it simply with analyze. It runs pretty quick. See, it finished running, so you have the results now. You can look at, for example, the losses. You can look at the temperatures. You can look at the currents, and you can look at the voltage. A lot of other things also can be added. You can add, for example, any parameter that you're interested in as a function of time. These are all the parameters you have. Let's say you want to calculate the power loss in these cells. You just plot it. See, it's pretty easy. I think just to summarize, we can say that This includes all the 3 YouTube shorts that we covered. We know that there is extensive research happening in the field of batteries. There's a lot of R&D budget going into that field, and we don't want to miss this opportunity. Solid state battery is the most promising technology so far, but it's still in the R&D stage. It's not ready for mass production yet. ANSYS can model batteries from cell to pack, either the known and mature technologies like lithium ion, which we have full capability, or even the new technologies, we can model it maybe by using some performance test data. All of them are pretty much doable. We know that Twin Builder can be used for modeling system behavior, which can predict what happens inside the cells and packs and module. And for BMS and ISO 2626 262 compliance, we can use Medini, Skate, and Twin Builder. And the last note is that ANSYS tools are totally compatible with third-party tools, but have better system-level metaphysics capabilities, which makes things faster and cheaper. Thank you all for your time and your attention. If you have any questions, feel free to let us know, and we will be more than happy to answer. Have a great day.